Hi, my name is Ansh Chabra, and this is my Lab 4 on circuits. The purposes of the lab were to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of resistors and capacitors. The models and fundamental physical principles of the lab were the conservation of energy and charge, the Kirchhoff circuit laws, Ohm's law, resistors and capacitors in series and parallel, the time dependence in RC currents, and capacitance. All the different models and fundamental physical principles are displayed by these diagrams on the right, and these are some of the equations that were used in the lab. The main results of the lab were that the current and voltage determined by the models matched what they would be predicted by the formulas, mainly because an ideal circuit was used, and also in an RC current circuit, current is time dependent and based on exponential equations. The system was the circuit and the surroundings were everything else. The initial conditions were the circuit with the batteries, resistors, capacitors, and bulbs, with all the given values, depending on the part of the lab. And the assumptions were that the wires had no resistance. The resistance of ammeters was negligible, and the EMF of the battery was the potential difference of the capacitors plus the potential difference of the resistors. The experiment took place in multiple parts. In the first part, there was two 1.5 volt batteries and two resistors of 47 ohms and 100 ohms and two ammeters. You would predict that the current on the first ammeter would be the same as the second one because of the node rule, and these were some of the calculations to get the current of 0.02. Replacing the ammeter with a voltmeter gave a potential difference of 3 volts with a zero current because open circuits don't have current and potential difference across the opening equals that of the power source. These were the potential differences across different parts of the circuit, and the total potential difference around the whole circuit was the sum of all the potential differences, which was 0. The ammeter value didn't change when the voltmeter replaced one of the ammeters because voltmeters have high resistances, so almost no current runs through them, so the current value measured by the other ammeter didn't change. And this graph on the bottom right depicted the potential differences at different parts of the experiment. Furthermore, connecting the ammeter in parallel with the 100 ohm resistor led to less current going through the 100 ohm resistor because of the split, so the current in the circuit increased. Those were the different resistance values at the different things at the 47 ohm resistor, at the 100 ohm resistor, and the resistance of the wire and ammeter. In the RC current with the battery bulb and capacitor, the bulb started shining bright and then it dimmed, and the current started at the max value and decreased to 0. But when it was just the bulb and capacitor without the battery, the bulb also lit up and then began to dim, where the current also started at the max and decreased to 0. The first with the battery was charging and without the battery was discharging. These were the values for how long it took to charge and to discharge. Here was the time-dependent voltage using the equations listed here, and that was the slope of the experimental data that we got. The theoretical RC was 6 seconds and the experimental was 5.96. This was the circuit we built in the lab, and the data matched the model almost precisely. The only source of error would be the error from humans in stopping the watch incorrectly, which would have resulted in the 5.96 seconds rather than 6 seconds. Other than this, the model matched the data almost precisely because of the computerized ideal model, and there were no significant differences in the data versus the model. What if this was done in real life and an actual ammeter was used instead of an ideal simulated ammeter? The ammeter would have had some resistance, so the ammeter would have read a smaller value for the current. And also, what if this was done in real life and a real battery was used to charge the capacitor with no resistor in the circuit? then the capacitor would reach full charge immediately, but that wouldn't happen in real life, because even if there is no resistor present, then wires have some resistance, so the capacitor wouldn't reach full charge immediately. Conclusions were that ideal circuits are slightly different than real-life circuits because ideal circuits assume no resistance in wires, which isn't the case, and also currents and voltages decrease exponentially in time.